Hi everyone. Today we're going to talk about the basics of probability theory. We'll have three objectives in today's slides. We'll learn how to calculate probabilities using counting outcomes in a sample space. We'll learn how to use counting formulas to compute probabilities. And we'll learn how to perform computations using the relationship between probability and sample space. Let's move on to distinguish between outcomes and events. An experiment is any observation of a random phenomenon. The outcomes are the different possible results of an experiment. Sample space is a set of all possible outcomes. An event is a subset of the sample space. Let's consider an example to illustrate these points. Suppose you want to flip a coin. Then flipping a coin is an experiment. The possible outcomes are heads or tails. So the set of all possible outcomes, which includes head and tail, is a sample space. An event could be the chances of getting either heads or tails or both. As a result, an event could be an outcome or the sample space itself. The probability of an outcome is a number between 0 and 1 inclusively. That means it could be 0.1, 0.2, 0.333, 0.456, and so on. The probability of an event is the sum of the probabilities of the outcomes that make up the event. Suppose E is an event, then the probabilities of E denoted as P of E is P of E equals to the number of times E occurs divided by the number of times the experiment is performed. Now let's apply the formula we just learned to an example. Suppose a group of psychologists want to test the effect of smiles on unexpected requests to people. They then proceed to approach 100 people, with a genuine smile of course, and ask them to lend $100. The results they obtain are summarized below. Out of 100 people they approach, 25 agree to lend them $100, while the other 75 did not agree to. So based on these results, what is the chance that a person would agree to lend you $100 if you are smiling genuinely when you ask them? Let E be the event that people agree to lend you $100. Then using the formula we just learned in the previous slides, the probability of E, which is the event people agree to lend you $100, is the number of times E occurs. Here is 25. 25 out of 100 people agree to lend you $100, divided by the number of times the experiment is performed. Since the group of psychologists approach 100 people, the experiment is performed 100 times. And therefore, the probability of E is equal to 25 divided by 100, which is 0.25. Now let's move on to how to use counting formulas to calculate probabilities. Counting techniques can be very helpful in calculating the probabilities of an event when listing the outcomes of an event is difficult, and we'll see very soon in an example how we could use counting formulas to do that. For example, drawing 5 cards from a standard 52 card deck, what is the probability that you will get a certain combination of 5 cards? According to the formula, the event E that a certain combination of 5 cards is drawn is P of E is equal to the number of times E occurs divided by the number of possible combination of cards, of 5 cards. And let's, for the sake of our lesson today, assume that we want to pick 4 twos and a 3 of hearts, and that is the combination of 5 cards we want to draw. Since they are a unique combination, the number of times that they can occur is 1. But we also need to count the number of possible combination of 5 cards, and it is in fact virtually manually infeasible. However, thankfully, from chapter 12, we know that there are 2,598,660 combination of 5 cards from a deck of 52 cards. How do we get these results? We use the combination formula. From 52 cards, we pick 5, and that would lead us to the result of 2,598,960 combination of 5 cards. Thus, the probability that we can pick 4 twos and a 3 of hearts is 1 over 2,598,960. That is extremely rare. Now, when we calculate probability, we want to know whether the probability we achieved is valid or not. And in order to do so, we'll compare it with the basic properties of probability. Let E be an event and S be the sample space. Then the probability of E must be greater than or equal to 0 and less than or equal to 1. The probability of the empty space is 0, and the probability of the sample space is 1. So we know that whenever we get a probability of an event that is outside of the range of 0 and 1, we know that it is invalid, and we need to recheck our methods and see where we make the mistakes. Let's move on to odds. Before we define odds, let's define the complement of event E, and we'll denote that the complement of event E as E with the mark, followed with the mark. For example, in flipping a coin, if the event E is the chance that we'll get heads, then the complement of the event E is the chance that we will get tails. So if the outcomes are equally likely to happen, then the odds against an event E is the ratio of the number of outcomes of the complement of E to the number of outcomes of E. Now we'll learn how to calculate odds. The odds against the event E will be equal to the probability of the complement of E divided by the probability of E. Let's consider the example, the smiling effect example that we had before. The odds against borrowing $100 is the probability of the complement of E, and in this case it's 0.75 because there are 75 people who did not agree to lend us $100, divided by the probability of the event E, and in this case is 0.25, which we calculated before, and thus the ratio is 3 to 1, and that's the odds against an event that people agree to lend us $100. And so that's it for today. Thank you very much.